Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And we continue our discussion into, limits at infinity. You have just finished watching a video, hopefully, on evaluating limits at infinity. That is finite limits at infinity. And in this video, we're going to focus on the theory behind that, which is incredibly important for you to truly understand how those limits work, like the true reason why they work. So we'll start with a definition that will ring very similar or sound very similar to what we did with epsilon delta proofs. The definition of a finite limit at infinity, the rigorous definition, assume that you have a function that's defined on an interval, and this one we're just dealing with x approaching infinity first. So let's suppose that we have a function that's defined on some open interval from a to infinity. Obviously, it doesn't have to just be a. It could go from negative infinity to infinity as far as its domain, but for this conversation, we'll just say a to infinity. Then the language limit as x approaches infinity of f of x is equal to L means that for any given epsilon, and now I'm going to start really talking about why we're talking about epsilons. So when we were dealing with, notice I'm not continuing with the definition yet. When we introduced ourselves to the precise definition of a finite limit at a finite point, we had this notion that the limit as x approaches not infinity, but a of f of x is equal to L, told us that for any given epsilon neighborhood about our limit L, there was a delta neighborhood about our limit a. That's the basic idea. Well, let me go ahead and I'll use green for the y value. So notice that the function and the limit, specifically the limit itself, the limit is finite. And so because it's finite, you're going to create an epsilon neighborhood, because around a finite number, like let's say 5, you can create a little neighborhood of values, 5 plus a wiggle and 5 minus a wiggle. Okay, that's the epsilon neighborhood. Well, likewise, and I'll use blue for x values here, if you were allowing your x to approach a finite number a, we could create a delta neighborhood, a plus a wiggle and a minus a wiggle. And so that would lead us to a nice little delta neighborhood. Notice in this definition, we again have a finite limit for the y value. So our y value being finite tells us we have an epsilon neighborhood. It's a wiggle about that y value of L, and we want our function to be within that wiggle. But our x value is not approaching something finite. Because x is approaching something infinite, x is going to be super large. And because of that, a delta neighborhood makes no sense. Like, you're not going to say, hey, well, what if I make a delta neighborhood about infinity? That's not going to work. Not like when you made a delta neighborhood about an x value of a. That makes sense. You're approaching a finite value. So you should have a wiggle to the left and a wiggle to the right. But you can't have a wiggle to the left and right of infinity. That does not make sense. So instead, you need to create an x value, or you need to find an x value that's super large so that you want all x values greater than that to have their function values be within the epsilon neighborhood of L. So punchline here is the following. If x is going off to infinity, then you'll want some number that's really, really positive that x is going to go beyond. Just like when we were dealing with the finite limit at a finite point, because x was approaching a finite value, you could kind of capture that within a delta neighborhood. Well, you can't capture infinity, So that's why we need to say, well, since x is going to infinity, I just want to find a value n so that for all x is greater than that n, my function's super close to the limit. Now I'm going to continue with this definition. So that language, x going to infinity of f of x equals L, implies that we're going to have an epsilon neighborhood. So for all epsilon greater than 0, there must exist an n super large. And I put this little subscript here. Let me showcase that. I put that little subscript there, or not subscript, but that function of notation, because generally speaking, you've probably noticed it with the epsilon delta proofs, that delta is a function of epsilon. In other words, when you found delta, it's always like delta equals epsilon over 17, or delta equals the square root of epsilon, or something like that. So delta was always a function of epsilon, not always, but 99% of the time, let's just say. And likewise, our number n here is also going to rely likely on epsilon. All right. So for any given epsilon that's positive, we are going to be able to find, hopefully, a very large value of n, such that whenever x is greater than that n, highlight that, our function must be close to L. How close? It has to be within our epsilon neighborhood of L. Notice my highlighting. I'm using yellow for the y values and blue for the x values. I'm just trying to keep something kind of clean there. Okay. So I think right now, rather than worrying about the second half of this definition, I think what I'm going to do is go ahead and just jump into an example. And then the second half of the definition, I'll jump back to, because I think that's a little bit better. So let's do that. So prove that as x runs off to infinity, e to the negative x approaches 0. Now, this is a theorem, actually. We've written this down as a theorem earlier on, actually in the last video. And now here we are going to prove it. The proof for any of these is actually really, really nice. We always start with scratch. So I'm going to write the scratch over on the right-hand side. But we also should have the definition of that limit at hand. And rather than having you memorize literally like 8 different definitions, I would prefer that you start thinking logically about whether you have epsilons, deltas, large values for outputs or large values for input. So let's just zoom in on this. The fact that our function is approaching something finite. I'm going to write the word finite in there. Since it's approaching something finite, I know it's going to be an epsilon neighborhood around that y value of 0. Just to give you a visual, you have this y value of 0. This is actually the y value of 0. And somebody's giving you an epsilon neighborhood about it, because you're saying your function's approaching that height as time goes on. So it might be something like this, okay? And so they're going to be able to capture that idea by saying, okay, well, I tell you what, how close to 0 do I want it to be? Oh, like this close, within this epsilon neighborhood. So that makes sense that they're able to band, or I shouldn't say band, I'll say bound, that they're able to bound your function within their epsilon neighborhood. So whenever the rule of thumb, finite value leads to epsilon neighborhoods for y values. Now, because of our x value is not finite. It's approaching something infinite. So I'm going to write that in there. And because it's infinite, it cannot be a delta neighborhood. That's critical. Delta neighborhoods are for finite values. Epsilon neighborhoods are for finite values. Infinite values, they deserve just super large numbers. So this is going to imply that we're dealing with a very large number. Super large, in fact. That's, oh, by the way, I forgot to mention, a lot of people, when I teach calculus, wonder, what does that double greater than mean? It means it's really, really greater than. It's like super greater than 0. It's a very large value. Now, armed with that information, I'm going to go ahead and write down the definition as far as the epsilon sort of delta definition of this limit. So I see I have an epsilon neighborhood, so I know it's going to say for all epsilon that somebody hands me, there must exist. Now I also see there's not a delta. So I can't say there exists a delta greater than 0. But I do see there's some large, super large n. So I'm going to say there exists a super large n. And I know it's a super large n because x is running off to a super large number. So I just want to find a super large n. Such that as long as x is bigger than that super large n, so I'll say x being larger than n, that will imply, and remember we do have an epsilon neighborhood, so the rest of it will look just like our regular epsilon delta definition. That will imply our function has to be really close to that finite limit L. How close? Within an epsilon neighborhood. So notice this is very close to the original definition of a finite limit at a finite point. It's very, very, very important that you can kind of bob and weave, that you can quickly create these definitions based upon the original definition of a finite limit at a finite point. Every single time that we encounter an example, I'm going to have this conversation. All right, let's go ahead and start to scratch. So let me switch to my red pen. The thing that we need to assume is this last little piece right here. We need to assume that our function is within an epsilon neighborhood of our limit. So I'm going to write that down. You should also notice that I'm trying not to be super excited, so I'm trying to slow down my speech a little bit. And I'll also say what I want here. What we want to arrive at, we're working our way backwards, so I want to work my way back here and find out what is that value of n? Like where can I start saying that x will work, and for all x values greater than some value of n, I need to find that n. So I want that x is greater than some super large number. Now, if you found that the epsilon delta proofs, which are the finite limits at finite points, if you found those to be kind of challenging but doable, then this stuff is going to be super doable because this stuff is actually super nice. So let's go ahead and work on the assume part. Our function is e to the negative x. And what it's approaching is 0. We want that to be less than epsilon. Well, this implies that we have the absolute value of e to the negative x is less than epsilon. Remember where I want to be. I want to get x to be greater than something. Well, notice here, I'd like to get rid of these absolute values. Well, exponential functions are always greater than 0, so I can get rid of the absolute values right now. E to the negative x is always greater than 0, so, e to the x is always greater than 0, so I don't need the absolute values. But now I can just take the natural log of both sides. So this implies that negative x is less than the natural log of epsilon. And now I'll multiply both sides by a negative so I can get x to be by itself. Remember what I need. I need x to be greater than some number. So multiplying both sides by a -1, I get x is greater than a negative natural log of epsilon. Now don't be fooled into thinking that this number on the right-hand side is negative. It's not. Nobody's going to hand you an epsilon super large. They're going to hand you a super small epsilon. And if you know anything about logarithms, you know that they look like this. And when you're plugging in values below 1, which epsilon is going to be, your natural log is going to be negative. So we're taking the opposite of a negative number, or in other words, this is some positive number, likely super large, especially if you choose a very small epsilon. The value will be very, very negative, and multiplied by a negative, it'll be a very, very positive number. So now I have found a number that x is greater than, and that number is positive, I promise. So let's go ahead and start our proof. Once we get what we want, we can start the proof. I'm going to keep that the definition in sight. Well, I'll zoom in and zoom out. Okay, so here we go for the proof. Somebody's watching in the wings and saying, okay, so prove to me that as x goes to infinity, e to the negative x is equal to 0. And I say, yes, I will, because you're going to hand me an epsilon. And they say, yes, I will. I say, good. how small of an epsilon do you want to hand me? And they say, as small as I possibly can, because I want to challenge you with a very small epsilon neighborhood. And I say, great, okay, fine. I could still force this function to go to 0 as x goes to infinity, I promise. Okay. Well, for all epsilon greater than 0, I personally will choose not delta. Remember, there's no delta in this definition. I'm going to choose a value of n, a super large value of n. I'm going to choose n to equal, let me look at my scratch work, negative natural log of epsilon. And whoever's challenged me, they're going to say, why would you do that? And I say, hold on, I'll tell you why in a moment. Now, if it is the case that x, just stealing my definition up here, okay? If it is the case that x is greater than n, they say, okay, great. You're just basically saying x is some large number, fine. It's okay. If that is the case, then it must be the case that x is greater than negative natural log of epsilon, because that's what I let n be. And they say, yeah, I agree with that. And you tell them, well, I'm glad you agree with that, because I'm going to multiply both sides by -1. And they say, don't forget to swap the inequality. And I say, I won't. There we go. And now they look at that and they say, that doesn't look like your function on the left-hand side. And you say, I know it doesn't, but I'm going to raise both sides base e right now. So this tells me I have e to the negative x is less than e to the natural log of epsilon. Well, e to the natural log of b is just b. So e to the natural log of epsilon is just epsilon. And they say, wait, that's very close to where you want to go, because they know you want to end up at the absolute value of your function minus your limit being less than epsilon. And right now you have e to the negative x, which is your function, being less than epsilon. And you say, yeah, we're getting there. Wouldn't you agree that e to the negative x is already positive? And they say, yeah. And you say, great. So would you agree that's the same thing as this? And they rack their brains. They look at that and they say, well, I guess it is, right? Because if I said 3, it's the same thing as saying the absolute value of 3. Or if I said 27, it's the same thing as me saying the absolute value of 27. So they kind of nod their heads and agree. And then you say, great. Well, wouldn't you agree that e to the negative x, though, is the same thing as e to the negative x minus 0? And they say, yes, but why would you do that? And I would say, because that guy right there is your function, and that guy right there is your limit. So I've successfully shown you that as long as I choose that n to be negative natural log of the epsilon that you hand me, and as long as x is greater than that n, I can guarantee my function is super close to 0. How close? Within your epsilon neighborhood. QED. Now, I do want to mention QED, that just means end of proof. It means quod erat demonstratum, so it has been demonstrated. I do want to give you a visual of this. So essentially what happened in this entire proof is that somebody said, okay, you're given e to the negative x, which looks like this. It actually decays a lot faster than that. I'm just exaggerating this. Okay. But you can see from the picture, it does tend to 0. Somebody walks in the room, they hand you an epsilon neighborhood. Boom, boom. The epsilon neighborhood's centered at 0 here. Okay, so it's the same distance above and below. Epsilon above, epsilon distance below. Our job was to find out for what x value onward will our function be in between these bars. And you can see from that blue line onward, our function is in between those bars, right? So our job was to find out what that point was. And we called that number initially this, n. It's a very large positive number. Right on this picture, it is not large, but that's because I have very large epsilon values. If they had really done their job, they would have given me a very small epsilon neighborhood. And so that n would have to be super large. But you should agree that for all of the x values that are beyond this blue line, all these x values from here onward, by the way, this is a proof that yellow and blue make green. So for all those x values from that point onward, their function values are within the epsilon neighborhood. That's exactly what we did. We found the n, that's the highlighted n up there, and all the x values that are greater than that n, we've just proven that the function value at those x values is within an epsilon neighborhood of our limit 0. Again, that is a really nice, clean proof. I would never show my scratch to the public. I would only show this ink right here without the business off to the side. Okay. And I wouldn't even show the highlighting. So it's a very clean proof without the highlighting. So now that that one is done, let's go ahead and look at the other direction. Like, how does the definition look like? What does it look like in the other direction? So assuming that f is defined on the interval from negative infinity to some value, all right, the limit as x goes to negative infinity of f of x is equal to L means that for any given epsilon neighborhood, and again, it's an epsilon neighborhood there because f is approaching something finite. So that implies that you have an epsilon neighborhood. There exists a super duper largely negative number. And again, it's not a delta neighborhood because x itself, let me use the right pen here, x itself is not approaching a finite number. It's approaching an infinite number. So you're going to have a very, very large number n, and it's going to be largely negative because you're going to negative infinity. So it's going to be very much less than 0. Anyway, for all epsilon neighborhoods that you're handed, you should be able to find some largely negative number n such that as long as x is less than that n, because x is going to negative infinity, so it's less than that negative number, the distance between your function and your limit is less than epsilon. It's almost the same exact definition, with the exception that in this case, x is less than a number rather than greater than a number, and that's only because x is going to negative infinity, and the number it's less than is not positive, it's negative. Otherwise, almost the same exact definition. So how does this work when you go to prove something? All right, so what I'm going to do here is actually use an example that wasn't in my lecture, just because I want to have us use the negative infinite limit here. So the claim is that the limit as x approaches negative infinity of 2 to the x plus 1 is equal to 1. And we want to prove that claim. A couple things I want to note here. Our function is approaching something finite. And because it's approaching something finite, that means we're going to be using an epsilon here. Our limit x is approaching something infinite, specifically negative infinite. So the delta is illegal. We can't do that. We can't use a delta. Delta neighborhoods are for small neighborhoods about finite points. So this will tell us the type of proof we're using. We know that we have some number, and that number is super duper negative. This gives me the view of our proof here, and I'm going to go ahead and write it down. The definition is going to be for all epsilon greater than 0, because we're dealing with an epsilon neighborhood. We have to find an n, not a delta, but an n, because again, deltas are reserved for neighborhoods around finite points. Specifically an n that's super duper negative, such that. Now, remember how the visual of this is. If you can keep visuals going in your head, that'll be very helpful. So the visual of this is that we have a function that's approaching a height of 1. This is y equals 1 as x goes to negative infinity. So our function might look like this, let's just say. All right. Somebody's going to come in and they're going to hand us a epsilon neighborhood about that y equals 1. That's a huge epsilon neighborhood, by the way. And our job is to find an n such that from that point backwards, so basically from that point to negative infinity, any x value we plug in will lead, oh, I highlighted the wrong thing, the x value to negative infinity. Any point that we plug in will, as far as x values, will lead us to a function value between those epsilon bars. And that's why in our definition, we require that for any epsilon somebody hands us, we can find a very negative number n such that x being less than n will imply the distance between our function and our limit should be less than epsilon. Or in other words, our function is within that epsilon neighborhood. So let's start some scratch work here. Scratch. And let's see, I'm going to assume that we have the distance between our function and our limit less than epsilon, and we want that to find an x that's, or not find an x, but find an n, so that for all x less than that, we get the function values to be within the epsilon neighborhood. So our function was 2 raised to the x. Was it minus or plus 1? I can't remember now. 2 to the x plus 1. And we're going to subtract the limit of 1. And we want that to be less than epsilon. And we start to manipulate this. We get the absolute value of 2 to the x being less than epsilon. I mentioned it previously, but the exponential functions are always positive, so there's no real reason to have an absolute value there. I want to get x by itself, so I'll take the natural log of both sides. When I do that, I get x natural log of 2 must be less than the natural log of epsilon. I divide by the natural log of 2, so I get the x is less than the natural log of epsilon over the natural log of 2. And I promise you that this is a negative number right here. Let me highlight it. This is totally a negative number because epsilon is going to be less than 1. Nobody's going to hand you an epsilon that's super large. They're going to hand you very small epsilons. So that's a negative number that we've highlighted. And there we go. I want x to be less than that. So that's our choice of n. So now I can just start the proof. So this is the negative proof, basically, negative infinity proof. So let's go ahead and do it. Proof for any given epsilon that somebody hands me greater than 0. Epsilon's very sloppy. Choose or let, whatever you want to say here, let n equal the natural log of that epsilon over the natural log of 2. Now, if it is the case that x is less than n, then by our choice of n, x must be less than the natural log of epsilon over the natural log of 2. I will multiply both sides by the natural log of 2, which is a positive number. So I don't have to swap signs. So this is going to be x natural log of 2 is less than the natural log of epsilon. I will bring that x into the exponent using the law of exponents, basically just following my work here. So this is natural log of 2 to the x. It's less than natural log of epsilon. Raise both sides base e to get 2 to the x is less than epsilon. And just so that we keep things kind of climbing this ladder, I'll just throw absolute values on that and then do this move right here. So this implies, because 2 to the x is already positive, I could say, well, that's the same thing as 2 to the x in absolute values. And I'll go ahead and say plus 1 minus 1 because, well, I can. And at this point, I will make a note to the world. This is my function. That right there is my limit. So I have successfully shown that for my choice of n, I can get the function within the epsilon neighborhood of that limit. And so therefore the limit has been proven or proved. So there you go. There's our negative limit. It works very, very similarly to the positive infinite limit. Now we arrive at one that I want you to know you do not always have to knee-jerk reaction and do a proof as far as epsilon deltas go to prove something. If you can use a squeeze theorem or something like that, that can be very powerful and used as proof as well. So here, we're being asked to make a conjecture about the value of this limit and then prove that value. So let me go ahead and show you a Desmos view of this. The double bracket x, you should recall, is the greatest integer function, and obviously y equals x. So greatest integer function is the red curve. It's not really a curve. I guess it is a curve. But anyway, it's the step function right there in red. And then y equals x is in blue. And you're taking the ratio of these values for any given x value. Now, if I zoom out a little bit, you could start to see that they kind of mimic each other. They almost get lost into one another as you zoom out. I can zoom out pretty far, and at this point, they look to be the same function. So in a way, not exactly, but in a way, the greatest integer function of x is the same, in a way, as x for very large values of x. It's not, because if I zoom in close enough, they're not exactly the same, but at a global or universal view, you can see they're pretty much the same. So if I were to take a function and divide it by itself, I would say that's 1. So that's what my claim is for that limit. So I'm going to claim that this limit is 1. If you don't recall the greatest integer function, just remember it is this function right here. I think we had it in a video previously because it's a very popular function in calculus and differential equations. But that function just returns the largest number, integer that is, less than or equal to x. So if x were an integer itself, then like if you plugged in 3, then it would just return 3. But if you plugged in 2.9, it would start to move left on the number line until it hit the number 2, and it would return the number 2. Okay? And in fact, that's a good way to think about it, because that's how I'm going to prove that this limit is actually equal to 1. Is I'm going to say, if you look at the limit as x goes to infinity of that picture right there, that's a troublesome picture. Because it's stepping. And so I'd like to bound it. I'd like to look at what is the greatest integer of x between. Well, it's always, think of, somebody in one of my office hours recently was asking a question. I just said, well, just plug in numbers and you'll see what the pattern is. And they were like, oh man, that is a lot easier. So I've always said it, but sometimes I forget to say it in a calculus course, but it's very important that you're able to take an example to help motivate an idea. So for example, if that x was a 3, well then obviously this would be equal to 3. If that x instead was a 2.9, it would not be 3, it would be 2. If that value was a 2.8, it would be a 2. If it was a 2.1, it'd be a 2. So the idea is that whatever we plug in, the maximal value it's going to be is what we just plugged in. That's the maximum it could ever be. You can try that out, but in the worst case scenario, it's just going to return what you plugged in. It's never going to return something larger. In other words, if I plug in 3.1, it's not going to return 4. It's going to return 3, right? In the worst case scenario, again, and even not in the worst case scenario, honestly, but it's going to return a number 1 less. It's not actually going to return a number 1 less, but it's going to return a number that is greater than 1 less than what you plugged in. Think about it. If I plug in 3, isn't 3 between 3 and 2, including 3? Absolutely. If I plug in 2.9, will it satisfy that inequality? If I plug in 2.1, will it satisfy that inequality? Absolutely. So it turns out whatever you plug in, it'll return a number that is at maximum what you plugged in itself, and at minimum, not including, would be that number minus 1. Okay, so this is going to be our bound for our greatest integer function. Now all I need to do is divide all 3 sides by x. So that will imply x minus 1 over x is less than the greatest integer function of x divided by x, which is less than or equal to x over x, which is 1. Now I'll take the limit as x goes to infinity. the limit as x goes to infinity on the left-hand side, so on x minus 1 over x. Well, you can do some algebra here. You can either break this into, I'll break it into two fractions. I'll use some algebra. Limit as x goes to infinity of x goes to x once minus 1 over x. And we know that this last one tends to 0 as x goes to infinity. And so therefore this is 1 minus 0, and that will equal 1. So the left-hand side limits to 1. We also know, that's the left-hand side. We also know the right-hand side, if you let x go to infinity, well, 1 remains 1. So the left-hand side and the right-hand side limit to 1, thus the center. The limit as x goes to infinity of the center, which is the greatest integer function of x divided by x, equals 1. By the squeeze theorem, you do have to mention that. So this is a really good use, again, of that very popular squeeze theorem. So you can't actually escape the squeeze theorem in calculus. It appears throughout all of calculus, Calc 1, Calc 2, Calc 3. So you cannot escape it. And I'll just zoom out to show that we are done with that. We have proved that that is equal to 1. I didn't have to do an epsilon delta proof or a precise limit proof here because the squeeze theorem takes over that. So if you have the option to use the squeeze theorem, that is a way to do proofs. Now, I mentioned in the previous video that we were going to come back to this problem once we had the epsilon or the precise definition of a limit for an infinite limit here. And now that we have it, we can come back here. Now, I'm going to give you a little bit of a fair warning. We are going to introduce a proof style here that you might not be strongly familiar with. So let me just tell you, there are proof styles that are, or maybe I should say, so I mentioned in the last video that we were going to go ahead and prove this or find the value of this limit in this video. And the reason why I wanted to hold off on doing that is because this limit doesn't exist, but there's no way to really showcase that using our previous mechanics. The only way you can prove that this limit does not exist is by actually proving the limit does not exist. And I'll give you a little bit of fair warning here. This involves a proof method that you may not have seen before. Let me just tell you what I mean by proof methods. The proof methods that you should already know how to do are the following. Direct proof, which is kind of a deductive proof method where you start with the if statement and you start throwing logical arguments in there until you arrive at the antecedent or the then statement. That is a very traditional proof style, direct proof. So if it's raining, then it must be cloudy. So you just start with the, well, let's suppose it's raining. Well, then there's moisture in the air. There's condensation. There should be enough condensation to collect enough moisture in the air at a certain elevation. And so therefore it must be cloudy or something like that. That is a direct proof. The second style of proof that you should be familiar with from your pre-calculus course is proofs by mathematical induction. And this is also known, by the way, as the domino proof. Well, I don't know if anybody else calls it that, but I do, domino proof. And I don't even know if I'm spelling domino correct. We'll do it like that, but I don't think that's how you spell it. Anyway, the domino proof. And that is used when you make a claim about that relies upon the natural numbers. So in other words, I claim that this is true for n equals 1, 2, 3, 4, and on to infinity, right? That's when you make a claim like that, that relies upon the natural numbers, then you're doing, to prove that, you would use a proof by mathematical induction. And if you've had pre-calculus, and if you've had a good pre-calculus class with a good pre-calculus instructor at the college level, then you have seen proofs by mathematical induction, and there's no need for me to continue forward. If your college instructor in pre-calculus did not cover that, then you need to email them and ask them why they didn't cover it, because it is required. So the next one, and I don't mind being a jerk, and I don't mind other professors yelling at me. They won't. They'll be ashamed. They should be. All right. So the next proof style is a proof by contradiction. And I shouldn't call it a style. I should say it's a proof method. And this method of proof is what we're going to use here. A proof by contradiction is how some people like to argue naturally. I don't know if you have any friends that argue by contradiction, but it is a very frustrating way to argue against somebody, because they say, well, let's suppose you're right. Then this would be true, then this would be true, then this would be true, and then the world falls apart. So that is a proof by contradiction, because they're presenting you with logical arguments, assuming what you've assumed. Well, let's assume that you're right. And then they prove you wrong by showing you that the end result through logical deductive arguments involves a contradiction or something going completely wacky in the end. It is a really cool way to prove things. It's also really frustrating. So not to prove in mathematics, but just to argue with somebody who argues that way. It's a great way to prove, though. There are other proof methods, but for right now, I'd like to introduce you to the proof by contradiction. So I'm claiming right now, just out loud, this limit does not exist. Mainly because I know this tends to 0, but this does not exist. And because of that, because one becomes finite and the other one wiggles on forever and ever and ever, right? Cosine just does this forever and ever as x goes to infinity. I know it's not going to exist. But if somebody said, prove that it doesn't exist, then I'd have to be very rigorous. So let's start that level of rigor. I would like you guys to just enjoy the ride here. So here's how it goes. Again, remember, I think this does not exist. Okay. So here goes the proof. Suppose, or better yet, I'll say assume. Assume that the limit as x goes to infinity of e to the negative 2x plus cosine of x is equal to some value. We'll call that value L. Now, we have recently been introduced to the rigorous definition of that limit. So if that is the case, if somebody says that's true, then I can say for any given epsilon, because again, our limit here, our function, is approaching something finite. So it has to be an epsilon. So for any given epsilon, there exists some large number n. And why do I do that? Because, well, guess what? X is approaching infinity. So we don't have a delta neighborhood. We have a super large number. Okay. So again, I'm just stealing the definition. So for all epsilon, there must therefore exist a very large number n such that x being greater than that n will imply f of x, or I shouldn't write that, I'll write it this way, implies e to the negative 2x plus cosine of x minus the limit must be less than epsilon for any given epsilon. Specifically, so this is the strong part. This is what's very important about that limit true definition. That if that's true, it's true for any epsilon I walk in the room with. You should be able to find an n. Well, the epsilon I'm going to walk in the room with is 1/10. You might be wondering why I'm choosing 1/10. It is because of that cosine. And you'll see in a little bit why I've chosen it, but I'm choosing it because I know cosine is always going to wiggle between -1 and +1. So I'm going to create an epsilon neighborhood smaller than that wiggle. I could choose 1/2. I could choose 4/5. I could choose 1/3. I'm just choosing 1/10 because I want to. No better reason than that. So let epsilon equal 1/10. Again, we are assuming this limit is true. Therefore, any epsilon should work. If somebody hands me an epsilon, I should be able to find an n so that x greater than n will imply the distance between our function and our limit is less than epsilon. So here's the epsilon I'm going to work with, 1/10. Therefore, we get the following. We should be able to find some value of n such that if x is greater than n, then the distance between our function, which is this guy right here, and the limit L is less than that 1/10 that we chose our epsilon to be. which will imply that if I multiply both sides by 10, 10 e to the negative 2x plus 10 cosine of x minus 10L should be less than 1. So far, so good. There's no logical break here. But since x is allowed to rush off to infinity, then e to the negative 2x will tend to 0. So I can make that disappear. I can just say, since x rushes off to infinity, that e to the negative 2x will eventually become small enough that we can just discount it. Now, this doesn't hurt the proof. It just makes it a little bit easier to work with the numbers. So I'm just going to go ahead and do that. But I'm just letting you know, it doesn't hurt the proof by making this assumption. In fact, keeping that 10 e to the negative 2x in there actually makes the argument more, it makes it easier to disprove this. So I'm actually sort of making it a little more challenging by doing this. So again, I made that disappear, and all I've done is shrunk our number down even further, basically. I've made it even a smaller number. I'm just helping their argument out by saying, oh, look, I'll even make it a smaller number. Now watch what happens. If I tell you that the absolute value of an object, this is not what I would normally include in my proof, but if I told you I have an absolute value of an object being less than 1, that means that object is between 1 and negative 1. So I'm going to trade out this absolute value for a triple-sided inequality. I'm going to say that is between 1 and negative 1. And now I'm going to just add 10L to all three sides. So let's go ahead and do that. And finally, I'm going to go ahead and divide everything by 10. And this, I'll actually just record me writing this down. So we're up to this point right here. By the way, I could have equalities on this, but I just chose not to. So it's not that big of a deal. It's totally okay. All right, we get down to here. Now, remember, x is moving on forever, right? X is allowed to go on to infinity. So what does that mean about the cosine? Cosine is going to take on all of its values. It's going to bounce between all of its values. Specifically, it's going to go between negative 1 and positive 1 forever. That doesn't disprove anything yet, but let's go ahead and see what happens here. Well, and maybe I shouldn't write implies. I'll instead say since cosine is between negative 1 and 1, we require that lower limit there to be roughly around negative 1. Better yet, we require it to be less than negative 1. So let me go ahead and write that in here. So remember, the cosine gets all the way down to and includes negative 1. But this piece is strictly less than the cosine, so it has to be less than, strictly less than that negative 1. And this piece over here, maybe I should use a different highlighter just to showcase that. The piece on the right-hand side is strictly greater than the cosine, so it has to be strictly greater than positive 1. That will give me two inequalities to work with. Let me go ahead and use yellow on this side too. It'll give me two inequalities to work with. So I'll say this implies that 10L minus 1 over 10 must be less than negative 1, and simultaneously, 1 has to be less than 1 plus 10L over 10. Now here's where our contradiction begins. Multiply both sides of both inequalities by 10. So I get 10L minus 1 is less than negative 10, and the other one tells me that 10 is less than 1 plus 10L. I'll add 1 to both sides of this first inequality, and I will subtract 1 from both sides of the second inequality. So far, so good. All of my mathematical logic is solid so far, 100% solid. And this tells me that L has to be less than negative 9/10. And you say, great. And at the same time, L has to be greater than 9/10. Now let me just draw a number line here. Here is negative 9/10. I'm requiring that L is less than that. Oh, by the way, here's positive 9/10, and I'm requiring L to simultaneously be greater than that. Do you see where the world falls apart? L cannot be simultaneously less than negative 9/10 and greater than 9/10. This is a contradiction. And this means that we made a bad assumption somewhere. Now let me scroll up to look through all of my arguments. So I started with this assumption. I assumed that the limit was finite, that it actually became something. Let's see if I made any other errors though, or if I made any errors. Well, if the limit is finite, this is just the definition of a finite limit at a finite point. No mistake there, none whatsoever. And this definition should be true for any epsilon. So me choosing one is not a mistake. I'm allowed to choose an epsilon. We should be able to find a large value of n such that as long as x is greater than that n, the distance between our function and our limit is less than that epsilon. Again, no break in logic there. I multiply both sides by 10. There's no mathematical break in logic there. Since x is going to infinity, it is true that this will tend to 0. Again, no break in logic there. So I just go ahead and replace 10 e to the negative 2x with 0. If I didn't, by the way, this number would not only be not less than 1, it would be worse, it would be larger. It would actually make this easier to break, essentially. So there's nothing wrong with that argument. Now I just trade out the absolute value for a triple-sided inequality. That's just basic algebra. Nothing wrong there. I added 10L to both sides, to all three sides, sorry. No logic break there. I divided everything by 10. No logic break there. I know that cosines between negative 1 and 1. And so therefore I know that since this is below the cosine, it has to be less than negative 1. And since this is above the cosine, it has to be greater than positive 1. So no logical break there. Well, since this inequality has to be true, let's go ahead and focus in on that. I multiply both sides by 10. No logic break there. Add 1, divide by 10. I get that. Okay, I agree. No break in logical deductive evidence right there. Same thing on this other side. Here's an inequality. Again, cosine gets all the way up to 1. I need this 1 plus 10L over 10 to be greater than the cosine, so it has to be greater than 1. Multiply both sides by 10, subtract 1, divide by 10. Again, no logical break, yet L cannot be simultaneously greater than 9/10 and less than negative 9/10. So I have reached a contradiction, and the only assumption that I've made in this entire argument is the very first thing, which is that the limit exists. My assumption was the limit becomes finite. Thus, so I'm going to write it down here. Thus, our assumption that the limit exists is incorrect. This limit is not finite. Now, at this point, somebody might say, well, we didn't prove that it's not infinite. Well, okay, I'm going to hand wave a little bit. It's not infinite because part of it goes to 0, and the other part, it only wavers between negative 1 and 1. So it definitely does not grow without bound. And that is somewhat easily provable, but I don't want to continue on the video with that. So I'm just going to go ahead and say this proves that this limit doesn't exist. It's a really, really beautiful proof style to argue by contradiction. And this is why, by the way, some law degrees require higher level math courses, specifically in symbolic logic, because you get to learn all the types of arguments. And mathematical arguments are very powerful. They're codified way, if you will, to showcase proper ways to argue and to really get people off their game. Anyhow, that's it. I should put a QED on that. QED.
It's It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.